Welcome back, guys. We are here with section 8.3 today. We're going to be talking about graphing rational equations, functions, and there are a few things to consider here because these graphs look a little bit different than anything we've seen before. So we're going to talk about some concepts, some discontinuities, places where the graph is not continuous. There's a break in the graph, and we're going to see some examples of those, and then we're going to get to just graphing rational functions. So let's get started. So there are three main types of graph discontinuity we are going to be discussing today. And then we'll hint at a fourth at the very end with our last problem. The first type of graph discontinuity is here in blue, the vertical asymptote. And what is it? Well, the vertical asymptote is what you see right here. I kind of have a semi-graph drawn already. It's this dotted line, and it almost acts like a force shield. That's how I think of it. I went ahead and plugged in some points. I said, okay, 0, if I plug in 0, we get 0 over 1, which is just 1. If I plug in 1, I get 1 over 2, so a half. 2, I get 2 over 3. Negative 1, if I try to plug in negative 1, notice I get negative 1 over 0, and we know we can't divide by 0. So that is going to be undefined. I plugged in negative 2. We get negative 2 over negative 1, so positive 2. Plug in negative 3, we get negative 3 over negative 2, so positive 1.5, 3 halves. And those are the points that I have on my graph, plus a couple extras. But here's what this graph looks like, and here's what a vertical asymptote is. Graph looks something like that. The vertical asymptote is that dotted line going straight up and down through x equals negative 1. And it acts almost like a barrier. You can see, I'm going to pull out a highlighter. My graph is going, it's going, it's going, it's going. It kind of tries to get as close as possible, but it never is going to go past that vertical asymptote. Same thing here. If we start on the right, go left, we're going, but it just veers straight down almost once we get close to that vertical asymptote. So that's what a vertical asymptote is, what it looks like. It often causes this very distinctive kind of swoosh. These two sides, sometimes they both go up, sometimes they both go down, but it's this barrier, this break in the graph, this discontinuity. When does it happen? When we cannot cancel something out in the denominator. So look at my function. F of x equals x over x plus 1. We know that we can't just do this because that x plus 1 on bottom, it's all connected, it's a single factor. So we have this x plus 1 on bottom. And so wherever that causes an undefined, that is my vertical asymptote. Vertical asymptote at x equals negative 1. That's how I knew it would be a vertical asymptote, because we had that in its fully simplified form in my function. We still had an x plus 1 on bottom. And so at negative 1, that means we're going to have our asymptote. And we will see examples of this more later on. But I want to give you guys a brief overview as well of our other two kinds of discontinuities that we're focusing on today. First one, point discontinuity, also more commonly referred to as just a hole in the graph. And you can see the graph I have drawn there, and it looks linear. And then right around x equals 3, there's just this hole in the graph, an open dot that kind of breaks up the graph. So what is going on here? Well, a point discontinuity, discontinuous at a single point, happens when the original function was undefined for x equals a, but we canceled that factor out. Let me demonstrate right here. We've got f of x equals x squared minus 9 over x minus 3, just rewriting it from above. And as we've said many times in this chapter, if you can, factor. You probably recognize that as a difference of two squares. x plus 3, x minus 3 over x minus 3. And then look at that, we can cancel something. X minus 3, x minus 3. So this function is really kind of just the function x plus 3. We know what that looks like. Slope of 1, y-intercept of 3, and that's what's shown on the graph. However, even though we canceled this x minus 3 out, that's not a good color combination, that kind of covers it up. Even though we canceled this x minus 3 out, it still has a part to play in the graph. It still causes an undefined, because if we tried to plug in 3 into the original, we would be stuck trying to divide by 0 again. So if we cancel something out, it's going to cause a hole. And wherever it would have caused an undefined. X equals 3, add the 3 to the other side. So if we can cancel something out, then it causes a hole there. We can graph the rest of the function just as normal and then draw an open dot there if we can cancel something out on the denominator. Vertical asymptote was when we couldn't cancel anything out. We had that x plus 1 still left in the denominator. That causes a vertical asymptote. If we can cancel a factor out, it will cause a hole in the graph or a point discontinuity. Okay, so again, we will see examples of these here in just a second, but we need to talk about our third type of discontinuity that we're focusing on, and that is a horizontal asymptote. Now, horizontal asymptote, we've actually already kind of seen in this video. If you look here at our very first example, definitely has a vertical asymptote there. But I'm hoping if you look closely, you might be able to see, well, it looks like there's a dotted line going straight across here that also kind of impedes the graph and breaks it up from top to bottom and causes that, you know, right here, it's this horizontal line that they're tracing as we go out to the left and the right. That is a horizontal asymptote. And when does it occur? It actually doesn't have to do with the denominator as much, undefines in the denominator. But here's when horizontal asymptotes occur. It depends on the degree of the numerator and denominator. If the degree, I'm looking in yellow right now. If the degree in the denominator is larger than the degree in the numerator, then we have a horizontal asymptote at y equals 0. No question. If the denominator is larger than the degree in the numerator, we have a horizontal asymptote at y equals 0. Let me show you what it looks like, then let me explain it. What is the degree on top? The degree on top in this is 2, because x squared is the largest power of x that we have. The degree on bottom is 4, because we have an x to the 4th down there. That's the largest power that we have of x. Degree on bottom is larger than the degree on top. That means horizontal asymptote at y equals 0. Now, if you're wondering why this is, horizontal asymptotes have to do with when we go to the edges of the graph. I'm going to start drawing in the air again. If you remember, I said, okay, so here's our graph. It has to do with this like line that they're almost both at as we go very far left, very far right. In other words, to use a concept we've talked about earlier in this class, it has to do with the end behavior. What is happening as we are going towards infinity? Well, I'm going to do some really bad math right now. This is not actual math, but it is useful for conceptualizing this concept. Infinity squared, if we plugged in infinity, which we can't do, over infinity to the 4th plus infinity cubed minus infinity, here's the truth of the matter. Infinity is pretty big, but it's not even going to hold a candle to infinity squared. On top, this infinity squared dwarfs everything else. It's so big. I mean, it's an ocean and these are drops in a bucket. So all we really care about as we go towards the end of the graph is the highest degree, infinity squared. Same thing down here. Infinity is big, infinity cubed is huge, but neither of them is even close to infinity to the 4th. Now, again, this is really bad math. Please don't tell any other math teachers that I'm telling you this. But again, for conceptualizing it, we have infinity squared over infinity to the fourth is kind of a simplification of this function. Using our exponent rules, we can divide two of the infinities out on top and bottom. We're left with 1 over infinity squared. That's 1 over a gigantic number. 1 divided by a huge, 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 huge number is basically 0. And that is why we get our horizontal asymptote at y equals 0. Now, if that infinity conversation didn't really make sense to you, that's okay. You can pause, you can rewind, you can rewatch it. At this point, you don't have to grasp why it's y equals 0. I think it's good for you to start thinking about it, and I want to show you the underlying reason. But for right now, it's sufficient for you to just know, look, if the denominator has a larger degree than the numerator, we're going to have horizontal at y equals 0. There's one other horizontal rule for us to look at, and that's in green down below. If the degrees on top and bottom are the same, there's a horizontal asymptote at y equals the leading coefficients. What does that mean? Well, look at our example here. Degree on top looks like it's going to be 3 because we have x cubed as our highest degree. Degree on bottom is also 3, so right there. Degrees are the same, top and bottom. So where are we going to find our horizontal asymptote? It has to do with those infinities again. Think about it. If we accept that the only things that matter are these highest degree terms, well then, let's look. What's 7 infinity cubed over 3 infinity cubed? We could divide out the infinity cubes. We're left with 7/3. We are going to have a horizontal asymptote at y equals 7/3. That's what I mean in green when I say it'll be at y equals the leading coefficients. 7x cubed, 3x cubed, those 7 and 3 were the leading coefficients, so it's going to be at 7/3. Okay, so I've covered a lot of new material already. Just right here are 3 main types of discontinuities we're focusing on. Vertical asymptotes, when we can't cancel things out in bottom. Holes or point discontinuities, when we canceled a factor out in bottom, and so we're kind of good to go there, but that canceled factor still plays a part. Wherever it's undefined, it's going to be a hole in the graph. And then horizontal asymptotes, which have to do with the degree of the numerator and the degree of the denominator. Let's put this into action. All right. I want us to find any horizontal asymptotes, vertical asymptotes, or holes in these graphs. Let's start with this first one. F of x equals x plus 3 over x squared plus 7x plus 12. Chapter 8 and the rest of your lives, really. If you look at something and it looks like it can factor, definitely factor it. X plus 3 over, well, set up my parentheses. X squared is x times x, plus and plus. And it looks like 3 and 4 multiply to be 12, add to be 7. I know I can cross those out. That tells me right now, I bet I have a hole. I canceled a factor out on bottom. So I'm gonna just mark that really quick. So we have a hole at, and I can see it's gonna be -3, because that's what would cause undefined with my x plus 3 factor, the one that I crossed out. Hole at x plus 3, okay. So that leaves us with 1 over x plus 4. I can't really do anything to cancel out that x plus 4 on bottom. So that means it's going to be a vertical asymptote. Vertical asymptote at x equals -4 because I couldn't cancel this factor out. The hole came from the one that I did, and then the vertical asymptote comes from the one that I couldn't cancel out. Lastly, is there a horizontal asymptote here? Look at the degrees. Degree on top, and I always look back at the original. Degree is 1 on top, degree is 2 on bottom. It's larger on bottom. That was our automatic rule then of y equals 0. And that's kind of a quick summary of our discontinuities in this graph. It has to do with factoring, it has to do with analyzing that denominator, and then the degrees. Let's try one more and then we'll actually get to the graphs. F of x equals x minus 1 over x minus 3. Is there anything to cancel out? And don't fall for the trap of saying, oh, x over x. Remember that minus, the minus 1 and the minus 3, link those together. That is one factor, x minus 3. So we can't cancel it except with another x minus 3. So there's nothing to cancel. So there are no holes in this graph, really. There is something still left on bottom. And so that indicates there will be a vertical asymptote at, where would we have undefined? What x value would we plug in for that factor? X equals positive 3 would make us divide by 0. And then degree on top is 1, degree on bottom is 1. They are the same degree, which means horizontal asymptote at y equals the leading coefficients. 1x over 1x, 1 over 1 is just 1. And so that's, again, how we can just, without even making a graph, find the discontinuities in our function. All right, so now is the exciting part. We've talked about these discontinuities, we've analyzed these equations. Now we're going to do it and actually graph a few of these. So we're going to do this first one together. Second one, I'm going to let you kind of try on your own a little bit. But this first one says graph the following function. X squared minus 9 over 2x squared plus 2x minus 24. As I'm sure all of you are doing now that you've written the problem down, you're saying, oh, this looks like it can be factored. X plus 3 over times x minus 3 over 2 times, I can pull that 2 out, x squared plus x minus 12. And so that actually looks like x plus 3, x minus 3 over 2, x plus 4, x minus 3. So factoring stuff out, because we know that's going to be really useful when looking for holes or vertical asymptotes. Right here, x minus 3, x minus 3, gone. What does that tell us? Because we canceled something out. We know there will be a hole at, what would make x minus 3 equal to 0? X equals positive 3. If we plugged in a positive 3, it would make that factor equal to 0, make us divide by 0. Okay, so took care of the hole. Just as soon as I cross something out, I like to do that to make sure I don't forget about it. Nothing else really to cancel out, so I would go ahead and say, okay, so it looks like there's going to be a vertical asymptote. I'm going to say vertical asymptote at, and it has to do with this guy we couldn't cancel out, remember? So x equals negative 4. Any horizontal asymptotes, we can kind of take a look here at my starting function. Degree was 2, degree is 2. So there is going to be a horizontal asymptote right at the leading coefficients. Horizontal asymptote at, we had 1x squared on top, 2x squareds on bottom, y equals 1/2. So again, this is how we can start getting the framework for our graph. I'm going to pull out a ruler and I'm going to say, okay, x equals 3. I know I have oh, that's a hole. I'll do that one in a second. 3. At x equals negative 4, I have a vertical asymptote. So I'm gonna draw that in. I have a horizontal asymptote at y equals 1/2. So I will get that right about there. So when we're graphing these now, wherever we have asymptotes and holes, those are the really interesting parts of the graph. Okay, Those are the really interesting parts of the graph, and that's where we want to focus on for our table. So it looks like at x equals -4, that's kind of right around the hot spot of where everything's happening with this vertical, and we'll see some action with the horizontal. We'll definitely have to go over to 3, x equals 3 so that we can see where the hole is. But I'm going to start by analyzing just right around here. So I know I can't plug in -4 because -4 would give me undefined. That's where my vertical asymptote is. But maybe I try -5 and I'll plug it into my simplified version. So that would give me -5 plus 3 on top. So that's, and then we're going to get 2 times -5 plus 4 on bottom. And let me zoom in really quick. So -2 over 2 times -1 is -2 equals +1. -5, 1, 2, 3, 4, 5, +1. What about -6? Let's try -6. -6 would give me -6 plus 3 on top. So -3 over 2 times -4 on bottom. So +3/4. So -6 gets me like +3/4, 0.75-ish. Now, I'm gonna guess that it's gonna look something like that. I mean, that's where it seems to be going. It's going down gradually. It seems like it's going towards that asymptote. I could always try -4.5, and I'll do this one by hand. We can use a calculator for this here soon as well. But if we plug that in, then we will get -4.5 plus 3, so -1.5 on top. And 2 times -0.5, so -1 on bottom. So that's +1.5. And sure enough, it looks like it's going to be shooting upwards in that rational function pattern. So I'm feeling pretty good about penciling that in. Let's see what's happening on the other side. I know that -4 is undefined because that was my vertical asymptote. What about -3.5? Let's do that one. -3.5 would give us -3.5 plus 3, so -0.5 on top over 2 times 0.5. So that's just 1, so -1/2. So -3.5 is -1/2. -3 would give us 0 over 2, which is just 0. -2 would give us 1 over 4, so 1/4. And again, hopefully at this point, you can see, okay, I see the swoosh. I know that my asymptotes are going to cause it to really, really do this and flatten out. My horizontal line towards the right there was a little wavy, but if I were drawing this smoothly, it would be just flattened out going close to that asymptote. One last thing to plug in. I know that there was a hole in the graph at 3, so I'm just going to draw the rest of the graph, then throw that hole in. This is how we can graph rational functions. So I'm hoping this made sense. It's quite a few steps. The graphing, like I said, I'll use calculator for that next one. But when you're looking at this, hopefully you see where the hole comes from. You see where the vertical asymptote and the horizontal asymptote come from. You felt okay about each step individually. Now it's just a matter of using muscle memory to kind of get all of that together and put it into one problem. So here is our second graph that we're going to look at today. Graph this function. I want to know about any horizontal, vertical asymptotes or any holes in the graph. I would like you to try this one on your own. I'm gonna start putting my work down and then unpause it when you're ready and you can kind of hear me talk through my work. So hopefully you had some success with this problem. Holes, none, nothing to cancel out. Vertical asymptote at x equals -3. Horizontal at y equals 0 because the degree on bottom was 2 greater than the degree on top 0. And this was an example of the table where we kind of both shoot upwards. It has to do with that squared in bottom. You'll start seeing some patterns. But hopefully, you know, once you made your table, your graph, I used my calculator for some of this. You can see it looks the same. If I go to the table, we can get points from there, which is a great time saver. But this is what this second problem looked like. So those two problems are the majority of what I wanted to show you as far as graphing goes. There is one more graphing problem though, and this is kind of this bonus concept that I'm giving you in this section. Here we have some familiar things. You can see on the right, there were no holes. I factored the function x squared minus 4 over x plus 1. So x plus 2, x minus 2 over x plus 1. When you factor it, there's still nothing to cancel, so no holes. There is a vertical asymptote at x equals -1. Degree on top is 1 larger than the degree on bottom, which is kind of interesting. We haven't really seen that before. So it's true, when I plugged these points in, there's not really a horizontal asymptote that they both go towards the end of the graph. So there's not really a horizontal asymptote. What there is, and I just wanted to show you one example, there is something called a slant asymptote. And it's like a horizontal asymptote, except it's slanted. It's a diagonal. These do exist. And so sometimes you will be graphing a function and you might say, oh, no horizontal. And then you notice they're both kind of, and this is hard to do with my hands, going towards the same line somehow. It's a slant. This is not super common. This is also not something you need to worry about as much as horizontal or vertical asymptotes down the line. I just wanted to show you one example of it, one picture of it, and really quickly, just extra bonus. If you want to know how do we find the equation of that slant, we're going to take the top and we're going to do some synthetic division. Remembering this from chapter 6, down, multiply, and we don't even care about that remainder. It's just going to be the slant is 1x minus 1. And you can see there, that's about what this graph is. -1, up 1 over 1, just about. This is supplemental right now. In class, we're going to talk a little bit more about it. In the video, I just wanted to show it to you, to show it exists and it's possible. And you might see it on some homework, some quiz. Again, I will clarify all this in class and go into a little more detail. But that is it for 8.3, guys. Lots of information, discontinuities, vertical asymptotes, horizontal asymptotes, holes in the graph, also a little bit this bonus slant asymptote. If you have questions, let me know. Watch, rewind, watch, rewatch these examples, and definitely get the practice problems, so we can build that muscle memory. But that is all for this section. Have a great rest of your day, and I will see you next time.